Hi, P-Psych. This is your Module 16 Basic Principles of Sensation and Perception. These are the first set of notes for Unit 4, which is our next unit. Don't forget that you'll have these as well as the Module 17 notes to complete before you come to class next. Here we go. So our essential question is, how do we process the information we receive from the environment? We have quite a bit of learning targets. So one, I can describe general principles of organizing and integrating sensation to promote stable awareness of the external world. This means that I can describe the principles associated with Gestalt, depth perception, top-down processing, and bottom-up processing. Today, our focus will be on top-down and bottom-up processing. Two, this is a large focus for today, I can discuss basic principles of sensory transduction, including absolute threshold, difference threshold, signal detection, and sensory adaptation. Three, I can explain the role of top-down processing and producing vulnerability to illusion. Four, I can discuss the role of attention and behavior. And then finally, we'll look at the work of major historical figures in sensation and perception of both Fechner and Weber, or Weber as it looks here. So first I want you to answer this question for me just based on what you know. Coming into this, we know this unit is sensation and perception. So I want you to describe to me, what do you think the difference between them is? So go ahead and write. Okay, let's see what you thought and how does it compare to what I have here for you. So here's the main difference. So sensation is referring to the biological processes. So as we go farther into this unit, you'll learn, for example, when we talk about vision, we're going to be talking about the anatomy of the eye and physiologically what is going on in both our eyes themselves, along with our brain that allows us to see. That is a biological process, would be considered part of sensation. So what that involves with any of our senses is detecting physical energy or some sort of stimulus that's coming from the environment, and then it converts that into a neural signal that our brain can understand and interpret. Okay. Kind of the main idea, and this will make more sense after I explain it to you, this relates more to something called bottom-up processing. On the other hand, the other part that this unit talks about is perception. And perception is much more of a psychological process. So it involves our selecting, organizing, and interpreting our sensations. So for example, for vision, it's one thing to have light enter my eye, and we have all of these different neurons that are sending signals via the optic nerve to my brain. Okay, that's the physical part, the biological part. But my brain has to interpret those ideas, those different signals that are coming in. And we'll see that that can change things pretty dramatically. So the way we perceive is very much based on something called top-down processing. And again, I know top-down and bottom-up don't mean a lot right now, but we'll be talking a lot about them both in these notes and with some things we do in class where that will make more sense. So for now, key thing, sensation is a biological process. Perception is the psychological process. So like I said, we're going to talk about top down and bottom up. I am going to do some activities with you in class that will help illustrate this even more. So after listening to this, if you're still a little bit confused, don't worry, I'm going to go back over it in class as well. So top-down processing is defined as this information guided by higher level mental processes, as when we construct perceptions, drawing on our experience and expectations. Okay? And a big part of top-down processing is using that prior knowledge. Things that, again, like the definition says, things that I've already experienced or my own expectations based on those experiences help me to figure out what I'm looking at, what I'm hearing, what I smell, what I taste. Okay. For example, if I were to give you a purple candy, Top-down processing would tell you that you're likely to taste something that is grape flavored. And the reason why you might expect it to be grape flavored is because of your previous experience and expectations. You've created an association between purple and grape. Okay. But know that the actual taste might not be grape. It's just what you expect. And you come to that conclusion because of top-down processing. If we look at this adorable little corgi puppy, okay, the reason why you know it's a dog, you can identify this really quickly, is based on your previous experiences and expectations. Corgis have gained a lot of attention in recent years, so many of you probably were very quick to be able to identify not just a puppy, but a corgi puppy based on those previous experiences and expectations. Okay. Another example down here. We perceive by filling in the gaps in what we sense. So being able to physically see the letters on the screen right now, that's one thing, okay? But being able to read what this says is because of top-down processing. I fill in those gaps based on my previous experience and expectations with these letters. So more than likely, even though I have letters missing from here, you can still read that it says, I want chocolate ice cream, okay? And again, that's because of top-down processing. Remember, top-down is based on our perception. Okay, so now bottom up. Actually, let me go back. So I'm going to give you another analogy. Think of top-down processing to give you something similar in terms of problem solving. Think of top-down processing kind of like a heuristic, very quick based on previous experience. Okay, now let's make that comparison with bottom up. That is going to be much more similar to, why did I just lose my word? An algorithm, there we go. To an algorithm, like a step-by-step process, okay? So bottom-up processing is defined as analysis that begins with the sensory receptors and works their way up to the brain's integration of sensory information. So we use the features, of the object itself to build a perception. Okay, and this is used when we have no prior knowledge. We have to start at the bottom, then work our way up. So, for example, when I showed this same image on the last slide, if you have no experience with dogs, you don't know dog breeds, it's just not something that you've had experience with, that you've been into, that you've been exposed to, you would look at this animal and your eyes are taking in the image that's striking your retina, and you start kind of working your way literally almost from the bottom up. So I start looking and go, okay, it's furry. It has a long snout. It has the ears like this. Okay, so I recognize all of those things. I think this is some sort of a canine mammal dog type. Okay. And you kind of work your way through each of those things that your eyes are taking in. Okay. Similar to an algorithm, if we're using bottom-up processing as our way to figure out, for example, what I'm looking at, or when I'm smelling, or when I'm tasting, this might take a lot longer to properly interpret what it is that I'm seeing, but it's likely more accurate than using top-down processing. Okay. Let me use the same candy example. If you'd never had experience with purple candy before, rather than jumping to the conclusion that it's going to taste like grape, you would actually put it in your mouth, maybe even close your eyes, and think about what sort of flavor or taste comes through. So it might be at first that this is sweet, and then you would work your way through whatever you think it tastes like. Okay, but likely it's sweet, and then you build upon, okay, what does the wrapper say? Does it give me some indication of what this flavor is supposed to be? And then you come to your conclusion. I meant to skip this slide. We're going to do an activity in class where I'm going to play some songs for you, and you're going to try to guess what the lyrics are, and then we're going to relate it to top-down and bottom-up processing. Meant to not put the slide in here. We'll do that in class. Okay, so question for you. What occurs when experiences influence our interpretation of data? Go ahead and select your answer. And you should have chose top-down processing. The key word is experiences. Okay, next idea we need to talk about is something called selective attention. And this is the focusing of our conscious awareness on one particular stimulus. So, as much as human beings like to think that we're effective multitaskers, in fact, we are not. We think we are, but we're not. When we're focusing on a particular stimulus, there are a lot of things that could happen around us that we don't notice. Okay. We're going to experience and play with this a little bit in class. When I see you, I'm going to show you some videos and different things. But for now, just think of that, okay? But I am going to tell you and give you a video of one example of selective attention, and this is called the cocktail party effect. Although this isn't an official vocab word, it is something that has appeared on the AP exam, so you want to make sure you write it down. And the cocktail party effect is defined as the ability to attend to only one voice among many. Literally, like if you're at a party, you're able to focus on one particular conversation, even though there's a lot of conversations and noise going on around you. Okay. And before I show you this video, know that the cocktail party effect can be particularly difficult for people with ADHD. They might not have that same level of ability as someone who does not have ADHD. So here you go, short little 1-minute video for you to explain.
What is the cocktail party effect?
It's this phenomenon where in the midst of a noisy cocktail party, any kind of noisy sporting event or newsroom, we're still able to focus in on the one conversation we want to hear and somehow tune out everything else.
And how can, now researchers, neuroscientists are very interested in this. Why is that? Why do they want to know where this ability comes from?
It's part of this whole phenomenon of selective attention, wherein the human brain can only really focus in intensely on one thing at a time. And this is a survival skill. You know, we're constantly bombarded by all this visual and auditory stimulation. We couldn't survive unless we could focus in like this, but we can also only really focus on one thing at a time. And that's what's at issue in distracted driving and all kinds of other limitations of multitasking.
Are there people who, is there like a small percentage of people who actually have sort of a super ability to focus on more than one thing, or is that a myth?
Yes, researchers at the University of Utah have found some of these people in the course of their other research. They think it's about 2% of the population. The real problem is that most of us think we can do that, and that can have some disastrous consequences.
Okay, so what I want you to think about is you could use, excuse me, that's what happens when I take a drink right before I have to talk again. Okay, you could use the cocktail party effect, or you can apply some other idea where you were so caught up in an activity that you missed something in your environment. So I want you to give me a personal example of that happening. Okay, so whatever you wrote down, I'm sure is a great example. We will play with this a little bit more when I see you in class. But just the idea that you were so focused on whatever task it was that you missed something going on. Maybe you missed someone calling your name. Maybe you missed something walking by. Maybe you, whatever it is. Missed a text message? Sure. So now let me give you some specific types of selective inattention. Notice that says selective inattention. Okay, so one type of this is something called inattentional blindness. This is where we fail to see visible objects when our attention is directed elsewhere. And I'll play a video of this for you. And then last is something called change blindness, where we literally fail to see changes in the environment. So inattentional blindness is visible objects. Change blindness is failing to see change in the environment. And I'll show you videos that describe both of these in class. And I think it'll be a little bit more clear there. So moving forward, before we can really understand anything else about the various senses, we need to understand this idea of transduction. This is going to be the foundation for understanding how do I take, for example, light coming in from the environment, from the outside world, and translate it into all of the things I'm able to see. Okay, and the reason that's possible is because of transduction. And transduction is defined, as this conversion of one form of energy into another. So with all of our senses, transduction has to take place. So as I just said, for vision, it's this change from literally from light energy entering my eye into a neural impulse that my brain can interpret and understand. With hearing, it's this change from sound waves into a neural impulse that, again, my brain can interpret and understand. With taste, it's a change in chemical energy from the food that I eat into a neural impulse. Do we get the point? With touch, it's a change from pressure, okay, into a neural impulse. With smell, again, it's a chemical reaction. So change from the chemicals entering my nose to my olfactory nerve that is changed to a neural impulse. Okay, so in sensation, it's this transformation of stimulus energies such as sights, sounds, and smells into neural impulses that our brain can interpret. Okay, there are 3 steps to transduction. So it's the receiving, transforming, and then delivering to the brain. So when we talk about each of the senses, a key thing we're going to focus on is when and where does transduction take place? Okay. Related to this idea, this one I don't expect to show up, but I'll tell you what it is anyways, is this idea of psychophysics. And this is the study of relationships between the physical characteristics of stimuli, such as intensity, and our psychological experience of them. So now we're going to spend the majority of the rest of the time talking about something called thresholds. Threshold is a word we've actually used before when talking about whether neurons fire or not. If you remember, a neuron has to go beyond a threshold in order to set off an action potential. That means it's receiving enough signals from other neurons that tell it to, yes, fire. So when we think of thresholds applied to our senses, I want you to think of it as what is the minimum amount, what is the smallest amount of outside stimulation before I can see something, before I can hear it, before I can smell it, before I can taste it, before I can feel it hit my skin. We're going to talk about ways to think about thresholds. There's some various I can't call them theories, but various ideas about what our thresholds are. So the first idea about thresholds was proposed by Gustav Fechner. If you remember, that's one of the names that we need to know. And Fechner said that human beings in general have a minimum amount of stimulation needed to detect a particular stimulus, such as light, sound, pressure, taste, or odor, at least half of the time. Okay. So if you think about us as people, he would say, what is the quietest sound? What is the least amount of sound waves, okay, that could be happening for you to be able to detect a sound at least half of the time? And he would say, whatever that number is, that is your absolute threshold. Okay. Another example for vision, where is the farthest something could be, like light could be, for me to be able to detect that there's light at least 50% of the time. Okay. So for example, how could we test your absolute threshold for hearing? Okay. If you've ever done a hearing test, maybe you've experienced something like this. They put some headphones on you and they expose each ear to various sound levels, various decibels. Sorry about that. I'm recording this during sixth period, or now at the end of sixth period. Okay, so for each tone, what they would do is they expose each ear to various sound levels, so various levels of decibels. It's the way we measure sound. And for each tone, the test defines where half the time you can detect the sound and half the time you do not. If you've ever taken a hearing test, you have to like push a button when you hear a sound. Sometimes they'll give you one in each hand. So when you hear it on the left, you push the left button. If you hear it on the right, you push the right button, and the audiologist can interpret those results. And they would keep putting it in one ear where that minimum level where you hear it at least half the time, that would be your absolute threshold. Okay. Fechner came up with some kind of general ideas of what he thought people's absolute thresholds were. You do not have to measure these. These are meant to serve as examples. So for example, for absolute threshold for smell, he said the minimum amount of chemical in the air for you to be able to smell is about 1 drop of perfume that's diffused into an entire 3-room apartment. And that would be the smallest amount of this chemical floating through the air that you would be able to detect that there was perfume at some point somewhere in the room. Okay. For vision, he said seeing a candle flame at 30 miles away on a clear, dark night, so a single candle flame, that you would be able to see that about half of the time, and that's the absolute threshold. That is the limit of you being able to see that distance away. Okay. For taste, he used the example of 1 teaspoon of sugar and 2 gallons of water. And for you to be able to detect like sugared water versus non-sugared water. Okay. For hearing, he said the tick of a watch when it's quiet otherwise, 20 feet away, that you would be able to hear that half the time. And then finally, my favorite example, I'm not sure how he came up with this, is the wing of a bee falling on your cheek. So a little tiny bee wing from a height of 1 centimeter that you'd be able to feel on your cheek that it's touched there. Again, these aren't going to show up on a test, but the idea is to understand what is the least amount that you can still detect half of the time. That's the key, 50% of the time. Okay, that's absolute threshold. Next, signal detection theory. So this is in reaction to absolute threshold. Okay, so this is a theory that predicts how and when we detect the presence of a faint stimulus, the signal, amid background stimulation or noise. Okay, the signal detection theory assumes that there is no single absolute threshold, so we can't apply those levels to everyone according to this theory. And instead, someone's ability to detect depends partly on a person's experience, expectation, their motivation, and their alertness. And what the signal detection theory is really trying to explain is why some people react differently to the same stimuli, or their reactions change as their circumstances change. So let me give you an example here of a newborn baby. Okay, I'll use myself as an example. I am not one of those people that you would consider to be a baby person. Okay, yes, I have kids. I love my kids. But I'm not the person that when I see a baby, I'm like, oh, please let me hold the baby. That's not me. Okay. I feel super awkward. I'm just not a baby person. I like older people. I teach high school for a reason. Okay. But when I have my kids, okay, my newborn infants, as a mom, you need to be able to hear them and wake up if the baby starts crying in the middle of the night. That's inevitable. Babies are going to cry in the middle of the night. They need food. They need diapers changed. They're going to cry. Okay. The other thing I didn't add before is once I'm asleep, I am out. Okay. I am not one that wakes up multiple times during the night. It's very rare. I am a very sound sleeper. Okay. So now with all that said, as a new mom, I need to be able to hear my children cry so that I can get up with them. Okay. When my kids were babies, I moved them out of my room into their own room with cribs and having a baby monitor when they were about 4 months old. Okay. I was able to wake up with them. Six periods over. I was able to wake up with them in the middle of the night and would hear them consistently, even though in other circumstances, I don't notice noises. Okay. And the reason why I was able to hear them, even though I was dead asleep, is likely because of the signal detection theory, because I knew I had an expectation and based on experience that my kids were going to cry in the middle of the night and I would need to wake up. So I'm going to be more attuned to, even unconsciously, listen for that sound that would wake me up so I could attend to their needs. Okay. That bottom picture, as a teacher, high school teacher, okay, I'm probably more apt to be able to hear subtle noises related to phones or to see things that look like phone use during class than someone that does not have my same level of classroom experience. And that's because I have the experience and the expectation and the alertness to look for those things. Okay. One more example, people that come back who have served in the military or in some sort of war zone, they are going to be more likely to detect and to be more sensitive to sounds that indicate danger, like gunshot or things that sound like that, than someone that does not have that experience. Okay. Another example of signal detection theory. Now, a few more terms related to these ideas of thresholds. So first is a subliminal threshold. This means it's below your absolute threshold for conscious awareness. So if it's subliminal, that means that it's below that minimum amount of sound, minimum amount of smell, minimum amount of taste that you can be aware of. And then finally is priming. Remember, priming is something we've talked about. It's going to have a similar meaning here. This is the activation, often unconsciously, of certain associations, thus predisposing you to perceive or remember or respond to something in a particular way. Okay. Like I said earlier, if I handed you a purple candy, okay, part of that, why you would expect it to be grape outside of top-down processing, is because of priming. You're unconsciously associated that purple candy with grape flavored things. Perhaps you had as a child other purple foods that were grape flavored. So you're automatically going to go in with that expectation of what you're tasting is grape. Okay, next is the difference threshold. Sometimes this is called the JND, or just noticeable difference. And this is the minimum difference between two stimuli required for you to be able to detect a difference at least half the time. I know that sounds way out there, but let me give you an example. Okay, let's say that you're in like your main family room, or lots of your family members come and go, and you're trying to watch Stranger Things. Let's say the new season has come out, you're trying to watch Stranger Things, okay? And you have the volume, let's say your TV volume is set to 15, okay, level 15. And as you're watching, either some siblings or maybe parents come in and they start singing very loudly, Don't Stop Believing by Journey. They start singing this song to the point where you're like, can't really hear your show anymore. So you turn it up to level 16 and you still can't hear what the characters are saying. So you turn it up to 17. Nothing, can't tell a difference in the sound yet. You might have to go all the way up to say 18 or 19 for you to be able to tell the difference, meaning you go from not hearing it to being able to hear it. Okay, that difference there is the difference threshold. Okay, also often called the just noticeable difference. Okay, so again, I went from level 15, then I can't hear it, and maybe I have to go all the way up to 18 or 19 for me to now be able to still hear it. Okay, that's the JND, or difference threshold. Last idea related to difference threshold is something called Weber's law. Okay. This is the principle that to be perceived as different, say two different sounds, two different things that you're. Sure I understand. Oh, Siri wants to get in on the action. Sorry. So this is a principle that to be perceived as different, two stimuli must differ by a constant minimum percentage rather than just a constant amount. So it would say like for my TV volume, rather from being able to go from like 15 to 19, I can't just tell everyone, just click up your TV by 3 numbers and then you'll be able to hear it. Instead, Weber's law says it has to differ by a certain percentage, okay, rather than an actual like numerical value. So for example, if we look at something like weight, if I have 2 different items, for me to be able to tell the difference in their weight, okay, if it is a 1 pound, no, let's go lighter than that, like a few ounces envelope, and then I have a second envelope that is just slightly heavier, because envelopes are already relatively light, that percentage I need to for it to feel heavier is fairly small. I decided rather than try to explain it to you, I'm gonna actually try to show you. I don't know how well this will translate, but I felt better having a prompt. Okay, so if I have 2 envelopes here, okay, if we were in class, I would have you hold these and do these yourself. Okay, so I have 2 envelopes. So the envelope itself, the weight is pretty similar. Okay, if I were to hold them both in my hands, trying to see if I'm on camera. Okay, if I try to hold them both in my hands, these envelopes would feel the same way. They're exactly the same, except in one of these envelopes, I have a little card that has some pennies attached to it. Okay, because the envelopes themselves are so light, I can put a 2% difference, and in the envelopes, it would be very easy to see. Okay, so no pennies or 1 penny, more pennies. Okay, this envelope, it's very easy to tell what envelope the pennies are in. Okay, now if I compare that to 2 books, I have 2 identical books, and one of the books has pennies taped in the back, the same amount as what's in these envelopes, and one of the books doesn't. Okay, because the books are so much heavier, okay, at first, even now, I don't know what book those extra pennies are in, because these books feel the same. So if I were to go just by numerical value, okay, I wouldn't be able to tell the difference. Instead, I would have to increase them by a particular percentage in order to tell the difference between the books. So if we open them up, one of the books has nothing. I'm trying to find where I put them. And one of the books has pennies. Okay, but by holding them up, you wouldn't be able to tell which is which. Okay. So now let me play this video for you that I think will be helpful. This was created, if y'all haven't noticed, I use his videos a lot, by Mr. Ray. He's the one that did our jump scare conditioning video and our Lego stop motion video. This is him in his car. He's going to use the car volume to demonstrate some of these ideas. So here you go.
Well, here I am in my car, and I'm going to use my car stereo here to do a demonstration of absolute threshold, difference threshold, and Weber's law. Alright, there's a song playing, and I'm going to turn it up very slowly. Right now it's on 0, volume is 0. I'm going to turn it up very slowly, and the second you hear it, it will have crossed your absolute threshold. Now the volume's on 1. Do you hear it? 2. If you hear it now, it just crossed your absolute threshold. It's on 3. Now you probably hear it. It's at 4. It probably crossed your absolute threshold. 5, 6, 7. I hope you can hear it by now. probably crossed your absolute threshold. So the second that you can hear something, or see something, or feel something, the second that you detect it, the second it goes from nothing to something, it crosses your absolute threshold. Difference threshold is when you can detect a difference in a stimulus. So if I crank this up to like 20, it's pretty loud. If I change it 1, it's hard to tell a difference. Can you tell the difference between 20 and 10? I'm sure you can. You can probably tell the difference between 20 and 10. If you can tell a difference when I turn down the volume, it's crossed your difference threshold. Now, it's easier to tell a difference between something like 5 and 10, right? 5 to 10. You can tell the difference. But I'm going to turn it all the way up to 25 and see if you can tell the difference between 25 and 20. Or how about 30 and 25? Harder to tell the difference when a stimulus is really loud, or really bright in terms of light, or really smelly in terms of smell. Well, here in terms of sound, it's harder to tell the difference between 20 or 30 and 35 than it is to tell the difference between like 10 and 15. Easy, right? Now 30 to 35. So that's Weber's law. Weber's law shows that it's easier to tell the difference between a low stimulus, and it's harder to detect a change in a really loud stimulus. There you go.
Okay. So hopefully that helped you to see the difference between those different ideas. Again, we'll talk about them in class and I can clarify for you if necessary. This is our last slide before we do some practice multiple choice. So this is sensory adaptation, and this is something I've actually brought up to you before when we talked about habituation, okay, in terms of conditioning. So sensory adaptation is our diminished sensitivity as a consequence of constant stimulation. I think the best examples relate to touch. So I gave you the example before of swimming. If you've ever jumped into a pool and it feels super cold at first, but then as you start swimming and you stay in there for a little bit longer, you don't notice it's cold anymore. What changed? Okay. The water temperature didn't change. What changed is now you've adapted to that feeling. You've had sensory adaptation. The other example I like to use has to do with underwear. Okay, a little taboo, but underwear. If you're sitting listening to these notes right now, you probably, unless they've shifted into a weird position, don't notice that you have underwear on, like you've stopped feeling them. And it doesn't mean that they have suddenly gone away. It just means that you've adapted to that sensation of them touching your skin, so you don't notice them anymore. Okay, that's sensory adaptation. So now I have some practice multiple choice questions for you. So first, what principle states that to be perceived as different, two stimuli must differ by a minimum percentage rather than a constant amount? Go ahead and select your answer. So the correct answer is Weber's law, or Weber's law. Next. What do we call the conversion of stimulus energies, like sights and sounds, into neural impulses? Go ahead and choose. The correct answer is transduction. Next, Natalia is washing her hands and adjusts the faucet handle until the water feels just slightly hotter than it did before. Natalia's adjustment until she feels a difference is an example of, go ahead and choose. Correct answer is difference threshold. Alternative answer could have been J and D, or just noticeable difference. Last question. Taishane went swimming with friends who did not want to get into the pool because the water felt cold. Taishane jumped in and after a few minutes declared, "It was cold when I first got in, but now my body's used to it. Come on in." Taishane's body became accustomed to the water due to what? Go ahead and select. And the answer is sensory adaptation. That is it for the Module 16 notes. Don't forget, you still need to do Module 17, which will be much shorter than these. I hope y'all have a great rest of your day.